interesting.
Okay, I think we're running here. One of our guest speakers on the screen said this is going to be an electrifying session. Let me tell you, gang. Our big, our big vlog featuring all of us on Mondays, 11 to noon in the rain. The rain has stopped a little bit now during our big Santa Barbara and California monsoon season. We call this the SBAU Astro Hour. It's on behalf of the Santa Barbara Astronomical Unit, your South Central Coast longtime astrophysics and telescope club, based right here in Santa Barbara, California. High-priced mud paradise, Santa Barbara's Museum of Natural History, where SBAU holds our first Friday of the month general meetings at 7:30 p.m. on the first Friday. It'll be a couple of Fridays away. We're going to have the very popular astronomy magazine columnist Bob Berman on the big screen inside Fleischman Auditorium. We also meet on the second Saturday of the month at our star parties. Have our telescopes out there at the museum's Palmer Observatory. You're invited. If you're interested in astronomy, you like this program because this is number 157. One more to go, and we start our fourth season, which the whole thing started 3 years ago on the first Monday of March in 2021. So welcome aboard, everybody. We're going to meet the gang here in a minute. My name's Ron Heron. In fact, let's meet. Oh, let me tell you what we're going to talk about. We're going to take a ride. Let me tell you, a brief sabbatical from the space race, the heavens. We're going to land back down here on Earth for some basic physics and a lot of math, electrons and protons, magnetism. Going to get heavy. Going to check out the waxing gibbous moon this week. NASA's plans to land Artemis 3 on the lunar South Pole. If you think magnetic fields and electricity is complicated, wait till we get up to the gravity between widely spaced binary stars. Good Lord, something called MOND, M-O-N-D. And the James Webb gets some corrections on those newly discovered distant galaxies. Plus, where's the missing dust? For crying out loud. I got plenty in my house. I'll loan the heavens. Let's meet the gang. Here's our President Jerry Wilson, beloved President Jerry.
Good morning.
He's our resident, I'm going to call him the professor of this class. This is like attending a physics class for an hour at Broydale Hall, for which they pay big money.
We'll keep it simple.
What?
We'll keep it simple.
What? Yeah, right. I couldn't even take notes because I didn't understand. I just gave that headline and didn't transfer much of anything. Nevertheless, Jerry's married to Pat Forgy, and he's been our president for 6 or 7 years. Chuck McPartland's been our outreach guy for SBAU forever. And I guess he's given up secretarial duties. His wife, Pat, holds the title of both merchandise manager for our club as well as treasurer. She's doing a bang-up job, and that's got to stop. Tom Whittemore is on board, editor of SBAU's monthly newsletter, barber science instructor out at Westmont College, and he's married to Maureen. And by golly, there's Tim Crawford, resident lens and telescope expert, who's going to help me out get through this electrical morass that Jerry's going to share with us here. He's married to Karen. How's all the wives doing, and the cats and the dogs? To get through this wet season? I like it better, I really do, than the drought. I love the fact that our reservoirs and lakes are full of water, even if it does leak sometimes in the house. So let's do our silly cartoons. President Jerry forwards these science cartoons, and I only got 4, but I have a feeling you're going to hit us with some that I either missed or from before. And we'll start the hour with a little levity, ladies and gentlemen. Here we go. Silliness abounds on the Astro Hour. See, there's one. All of modern astronomy versus stellar astrophysics. It's a Jenga game. Remember that Jenga with the blocks? Isn't that what
All
it's called?
balanced on one thin stick here.
Okay, that needs some explanation. Stellar astrophysics is more critical than all of the rest of astronomy? I don't get it.
No, it all goes together.
Oh, it all goes together, but
this is a major pillar of astronomy, stellar astrophysics.
Okay, it could be like dark matter. We just be careful, don't.
No, this is the part we know about. The dark matter, dark matter is just a phrase for I don't know. Think of dark matter as je ne sais quoi. It's I don't know in French.
But stellar astrophysics is just the stars or just our solar system?
It's how stars work. Everything's based on that. The
Okay,
fusion of core of stars.
that's a great cartoon. Okay.
Yeah.
Here we are, the bats from hell hanging out. See, this is from last week. Two bats are hanging in a guano-stained cave, smelling like you wouldn't believe it. Yeah, he says to the other, you know what? You got fireflies stuck between your teeth, Bob.
I didn't get that. Okay, now I get it.
For the rest of us, it's spinach. Now, here is, this is held over from last week. Very nice of you, the guy says as he descends into the basement, of all of you to try and help, but I'm afraid this isn't the type of dark energy we were looking for. It's all the other dark things of history in one dungeon. A 5 MB, what does MB stand for? Hard drive being shipped by IBM 1956, and that wasn't even Amazon. That's a piano, isn't it?
No, that's the disk drive.
Is it really?
They used to call it, I think they called them drums.
Okay, and back then IBM was the Amazon.com of the era, I
Yeah.
suppose?
They,
Okay.
I had heard somewhere along my career that a marketing study done by IBM predicted that the world demand for electronic computers was at 5. Once you built 5 of these computers, that would satisfy the world demand for computers. Are you guys frozen or?
Ron is. Ron is. You're not, Jerry.
Yeah, you're not either, but Tim Crawford is.
Tim is and Ron is.
Okay. Okay. Little technical difficulty here.
Hmm.
Oh, one of them bailed off.
We lost both of them.
Oh yeah. Okay. Well, anyway, this is in honor of Valentine's Day.
Yeah.
The aliens have figured out that we give these as little messages of communication. So, and here we have a statement reminiscent of the wine country. It's only physics if it comes from the physique region of France. Otherwise, it's just sparkling math.
Tim just texted me they lost power, so maybe that happened to Ron too.
Okay. Here's XKCD's view of the existence of an 800-meter sphere that tastes okay. So this is a graph of how tasty things are. Down here, the moon is not very tasty. Up here, grapes are real tasty and melons. And the sphere diameter is real small here. This is grape size and this is green. So the large area in between is empty. So there must be something in there to fill it up. Okay, we're back to the start again.
Okay.
So that must mean the Baron is off too.
Yeah.
Yeah, okay, bummer. Okay, stop sharing and go to, get rid of these. Go here. No. Why am I having so much trouble here?
It's one of those days.
There we are. No, we got the talking points all right. Let's go to
Lorentz scores.
Yeah, somehow I've hit a button and it has turned my entire table upside down. So number 1 is at the bottom. Let me see if I can flip that over again. Content times details. No, it's not going to work. I think AI has taken over. It's smarter than I am.
There was
Okay.
just a report that Air Canada was testing out using an AI chatbot to help when it got busy, to help with customer complaints. And some lady, you know, had a death in the family, and she was trying to arrange for bereavement fare, and so she ended up with the chatbot, and it basically just made up a rebate for her. It just said, "Oh yeah, you know, if you do this, you know, it'll only be half price." And Air Canada tried to weasel out of it by saying, "No, that's not true. The AI chatbot is an entity, a legal entity all unto itself, and so it's responsible for making that mistake, and we don't have to honor this bereavement discount." And she took him to court and won.
I'll bet that's an employee of theirs.
Yeah.
Okay, now I can't get you guys back.
Mhm.
Oh no, we're fine.
Yeah, we're on the edge here.
Yeah. Can you see these equations?
Yep, now I do.
Okay, good. These are simple equations simplified for electrostatics on the top. It's a vector field, an E field. And then the B field is the symbol that's used in physics for magnetic field. They're very similar. The little things out front, the Q over 4 pi epsilon and the mu Q over 4 pi, those are just terms in the front to make the units come out right. So there's not a lot of physical meaning there. The key thing is that electrostatics, the electric field, is inversely proportional to the square of the distance between the observer and the charge center, where it starts from. The magnetic field also has the inverse square distance, that if you're twice as far away from it, it's 1/4 the amplitude, but it's velocity dependent between the observer and the source. If the observer is moving at a speed v with the source, you see a magnetic field. If the observer is fixed and the electron, say that's the source of it, is moving by, then you see the magnetic field move along with the electron. If the electron is stationary and you're flying by the electron, you see a B field associated with the electron. But if you stop next to the electron, you don't see any magnetic field. Magnetic field is a dynamic thing. Whoops, went the wrong way. Okay, now this is a representation of
There's Tim. Tim's back.
Okay, good. Welcome back, Tim.
Yep, I'm here.
This is a representation of a dipole. There's a positive charge, say a proton, and there's a negative charge, say an electron. And the convention is that electric field starts on the positive charge and moves toward the electron or the negative charge, where it goes there and it stops. So there's a source of a charge. These are each called monopoles, and the two of them together is called a dipole. There is no such thing as a magnetic monopole. Magnetic fields, magnetic fields they're all closed loops. They don't start anywhere. Now, these are not single discrete points like an electron and a proton. This is a coil, a loop of wire with a current in it. And so it comes out of the page and back into the page. It's just that it's cut off here to show the cross-section of the wire. And the dot in the middle of the wire is a physics convention for an arrowhead pointed right at you. And this is the convention for an arrow's tail or feathers pointing away from you. So the current in this thing that produces it, the moving charge, the velocity component, is due to a charge going into the wire here and circling around and coming out here. So it's a closed loop of current. It's got to be a battery in it somewhere, but that just complicates the picture.
Right. And Jerry, if you want this, you know, if you use your right hand and you stick your thumb in the direction of these arrowheads, with the curl of your hands, they represent the curvature of the field.
Right. That's the right hand rule.
Mm-hmm.
And so every line here that goes up comes back around and is complete there. And now in the sun, where there's a lot of ripped apart atoms, there are no whole atoms in the sun. There are it's basically the first order of plasma with everything ripped apart. There's a lot of currents flowing, so you can get very complicated loops and all of the phenomenology that follows from that. Oops, okay. Got to learn to go the wrong way here. Now this is a series, this is a coil, like a spring, and it's coming out of the page on the top, the circles with the points. Those are the arrows for the current coming out. And this is how you magnify, get stronger magnetic fields by wrapping more coils around it. And the crosses down here are current going into the field. And they do not, trust me, I'm not going to trace them all the way out, but they do not, they do not close. They do not stop. They're closed loops.
Right.
Can you
Often called a solenoid, right, Jerry?
Yes, yeah.
Can you hear me?
Yes.
I want to thank Southern California Edison for that, cutting me off. Don't ever let anybody tell you, gentlemen, you're in total control. Just tell me what the round circles are. Atoms?
The round circles, this is a coil of wire, like a spring, and it's been cut off. So you see each wire as a round thing because it's been cut here. And the dot is what physicists use for the point of an arrow sticking out of the page. It represents current flowing toward you as you look at this diagram. This cross down here represents the feather side of the arrow, and it's the current moving into the board or away from you here. So current is going in at the bottom and coming out at the top and then looping around at the part where you don't see here. So these are current loops. And
but they only go in a direction of a certain polarity, right? They go toward positive or negative. That's not even a factor here.
The electric charge and what drives current is that, and the difference between magnetic field and electric field is that the electric field starts on a positive charge and it ends on a negative charge. So magnetic fields don't do this. There's no magnetic monopole. These are electric monopoles. This is a proton, for example, and this is an electron. Or this is a sphere with a lot of electrons on it. This is a sphere with a lot of electrons missing. So you can generate positive and negative sources. So these are monopoles. There is in this universe apparently no magnetic monopole. There have been many experiments to try and find one. There's one theoretical statement that it should exist. The Dirac equation says if there's even one monopole, magnetic monopole, somewhere in the universe, then things can be, you can understand quantization. That's a long argument, but
Ron, these should not be confused with tadpoles.
Thank you.
Well, that I get.
Thank you for clarifying that. Is this what a battery is then?
This is we'll get to batteries.
Okay.
This is a single loop of wire with a current coming out of the page here and into the page here. And this is the magnetic field that's generated around it. It doesn't start anywhere or end anywhere. It's just a continuous loop.
Okay.
And in order to keep this current going in the wire, you have to have, it's either a superconducting coil with a current going in it, or you have a battery to maintain it. So let me go back here to these little puppies. You were,
oh boy.
So this is electrostatic field, the E field, and this is the B field, the magnetic field. You can forget these little beasties out front because those are just constants to make the units come out right. This is the charge on an electron, charge on an electron. The electrostatic field is dependent on how far away from the source you are. The strength of the field drops off as the inverse square of the distance, just like in gravity. It drops off as the square of the distance. It's a geometric effect. The B field has similar formulation to the electric field, except it has a velocity in here. If nobody's moving, there's no magnetic field. You have to have the charge Q moving. So if you take the charge, a lot of charges, and the velocity, That's the current, I. And so it's the magnetic field is equal to I crossed into, this is a mathematical expression called a cross product. And this is where the right-hand rule comes in. If you put a charge in an electric field, the charge pushes it along on the lines of the electric field. If you put a charge in the magnetic field, it doesn't push it along, it moves it to the side. That's what the cross product does.
Really?
So the math is different, but the formulation of the equations is very similar.
But it all involves, since the word electricity is kind of close to electrons.
Yeah.
We're not talking about moving protons at all. They just sort of stay out there, and
No, you can move protons too.
it does.
Yeah. They tend
Jerry,
to bring
what is that
along.
in the top equation? Is that epsilon with base 0? Is that what that is?
Yeah, epsilon 0, that's the permittivity of free space. So take that as 1. And this is the magnetic permeability of free space, or whatever material you're in. So the key down here is that if you're standing on a street corner and an electron is driving down the street, as he goes by, you will see around him, you will see a magnetic field because he's traveling at a velocity v. If you are moving with respect to a parked electron, but you're moving down the sidewalk, you will see a magnetic field around the electron because you're moving. As long as someone's moving, you get this effect. If they're both stopped, if you're standing stopped next to a parked electron, nobody sees a magnetic field. Magnetic fields due to the motion.
So E is, you called it an electrostatic field, but B is called what?
B is called the magnetic field, just for, it's actually the magnetic inductance density, but that doesn't matter. It's the magnetic field. And in materials, this is in space. In materials, we use the capital letter D for the electronic displacement vector, and we use the capital letter H for the magnetic displacement vector. But these are the fields in free space.
Tim, if you had just, if you were able to pin down an electron, okay, and ask about the electric field, it would look like spokes on a bicycle wheel going straight out. Okay.
Yeah.
Actually, they come in for an electron, but they go out for a proton by convention.
Well, is it safe to say, or fair to say, gentlemen, that in a long wire, one little electron or any of the electrons don't travel the distance? They jump, one jumps to another atom, and then it jumps from that atom. Isn't it haphazard?
Yeah, it's a crowd. You push it and it's full. You push a fat lady in at this end and someone has to pop out at this end, but it wasn't the same person you pushed in up there.
Right, right.
And
So,
I used to argue with the guy at the radio school I went to 50 years ago about that. I said that thing you just described, popping in at one side, and he said it was instantaneous. I said, no, it'd have to go the speed of light. Can you solve that once and for all for me? Does it still go up the wire the speed of light?
it doesn't go that fast.
They don't do that.
No.
They don't even go that fast. Oh.
No.
The signal goes at the speed of light.
The signal goes, Ron, if you were to put your finger on an electron moving down a wire, okay, it's crawling at the speed of an ant.
Yeah.
You can actually watch it.
Really?
But like Jerry said, it's the signal. The signal goes,
Right. It's
well,
like
speed of light divided by the medium.
it's
you know.
like
So it is a fat lady.
yeah, it's like clean the whole wire out. It's like looking at a wave on the ocean. The wave comes in and crashes on the shore, but the water that's in the peak of the wave when you see it out in the ocean is not the same water that hits the beach. This is the distortion that travels through the water.
Oh, okay.
But this instructor used to tell me it's simple. It's a big long pipe full of marbles, and if you put a marble in this end, one has to pop out at the other end. And I told
That's
him,
true. That's
it's like
true.
train cars. Once the engine gets going, it's got to be passed along.
Yeah.
You hear it go chunk, 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 chunk. You know.
Sounds like he took you for a loop.
Yeah. Okay, so this is a single wire with a current flowing in it. And this could be a jet or a stream of plasma on the sun. And this is the current I, which is the flow of positive charge.
Right.
Never mind.
Very important.
Right. The convention was decided on before they figured out what it was that was actually moving.
Mhm.
So the electrons are going this way, the current goes this way, and the B field is a circular thing around it
Mhm.
that falls off as the square of the distance.
Wow.
I think it
No.
falls off as 1/r, Jerry. Check me on that.
Now that basically is how we
On
get
a
up
wire,
there.
I think it falls as 1/r.
Oh, it could. Yeah, you're
By
right.
Biot-Savart law.
Yeah. Yeah.
Is that a turbine we're looking at? Is that how
No.
we get our electricity?
No.
Now
That's
this is what's called the Bohr atom. This was what Niels Bohr proposed as an atom at the beginning of the 20th century. And it's still used today in beginning atomic physics because it illustrates the energy levels that electrons take on. This is the nucleus, which has the atomic number times E, but in for a number, but in positive charge in the middle, and negative charges out here. And why did I have this in here? Okay, well, it'll come to me in a minute. Oh, yes, that's right. So this electron going around here or around any of these orbits, that is the equivalent of a single charge going down here as a wire. That is, a single charge going through will produce this B field as it passes this point. If you're standing down here, when the electron passes you, you'll see this B field all of a sudden be there and then be gone as it travels around there. So in a Bohr atom, this thing runs around the circle and it creates a magnetic field that it is a loop. And so the magnetic, if it goes, say, counterclockwise around there, then the magnetic field comes up. This nucleus would be the point of the arrow coming up where the magnetic field comes up. It creates a magnetic field around it. And those magnetic fields, this one is called the Bohr magneton. This is for a single energy level in the lowest energy level of an atom. It's also true that things with spin have a magnetic moment also, very small magnetic field. And then we get into the realm of whole materials. And this one, we're going to pay attention to one on the right, or the left, I mean, the right one we're going to ignore. This is ferromagnetic material. And this is where all the magnetons, all the magnetic moments of each atom in the material, say iron, they all line up and they freeze that way. And so this material has a permanent magnetic field. It doesn't have a externally applied current that makes the magnetic field. It depends on the spins inside the material and the orbitals inside the material because they're all lined up. So the magnetic fields add up. Now, if you take that material, when it's molten, when iron is molten, it has all these atoms in it, but they're all helter-skelter pointing in every single direction. If you pour it out into an ingot or a flat something, and as it freezes, it will line up with any externally applied magnetic field, and that will freeze in. So that's where you get permanent magnets. And in the Earth's magnetic field, you pick up the 1 Gauss field that the Earth has, and the material will point in that. Once you pick the material up, it of course no longer points in the direction of the Earth's field because you've moved it, but it has a preferred direction and it's a weak magnet. When they make ferromagnets for the horseshoe ones for school and for kit toys and stuff, and for other uses, they let the material freeze or set in a very strong magnetic field, so it becomes a strong magnet. So yeah, go ahead.
one side is not, it's supposed to be north, the other is supposed to be south, but that doesn't.
Points north.
Points north.
North and south.
Is another word for ferromagnetic materials any metal?
No, only ferrous metals.
Oh, so your mercury, your tin, your titanium, they don't qualify?
No, they don't. The aluminum will not become a ferromagnetic material.
Really?
Aluminum actually is a diamagnetic, which means in the presence of a magnetic field, its little electrons try to run backwards and blank out the magnetic field. But that's a whole nother story. So,
Jerry, does the strength of a magnet depend on the strength of that one that's charging it? Is it?
Yeah, it picks up the strength of the up to a limit. It picks up the strength of the magnetic field. Some things they're rigidly aligned like this. That'd be a very strong magnetic field. With a lot of tilt to it and stuff, it would be a weak magnetic field. If you take a permanent magnet, say of iron, and you hit it with a hammer, the shock of the shock wave going through it re-randomizes the field, and so the magnetism is lost. And if you melt it, it also is lost because the heat is randomization of the motion.
We used to magnetize a piece of metal by just taking a magnet, like your horseshoe magnet, and rub it in one direction, and then it would magnetize it.
You can take a nail and put it in a coil with a strong magnetic field on it, and some of the stuff will line up and create a magnet.
Okay, I've seen
That's how you remagnetize a magnet.
Gosh, I'd really like to study this. This is fascinating.
So what happens here in application of that? This is the lithosphere on the Earth, the seafloor, underwater, because we don't want any continents in the way. So magma comes up from inside the Earth, and it's got the core of the Earth, and it has a lot of magnetic materials in it. And so it comes up here as magma, and then it spreads out. And as it spreads out, it cools. Well, it's in the Earth's magnetic field. And so it picks up the direction of the Earth's magnetic field. Well, years ago, the field was reversed. And so you get a different magnetic orientation here, different strength and different direction. And the direction alternates between these things. These document the Earth's magnetic field switching polarity. So this is, the white is reversed magnetic polarity. The normal magnet here, the red, is stuff that's now picking up the current magnetic field. And these are ones, older magnetic field. They're still strong, but they represent a different orientation slightly.
Is there a relationship between this switching of magnetic field to the sun and its switching fields?
No,
not at all.
There's an analogy, but no direct comparison.
Okay.
Ron, a lot of this was discovered in the Second World War. We started, probing the ocean floor and seeing this banding and stuff.
Well, Jerry just said years ago it switched. That wasn't while humans were alive, was it?
Yes, it switches. I think the switching happens every couple of 100,000 years, and human hominoids, whatever it is, has been on the Earth for 1 million years, and I think Homo sapiens has been on for about 300,000.
Okay,
don't quote me on that. It's not my expertise.
All right, here's a basic question you probably already covered. N and S, north and south, is that the same as plus and minus?
No.
Nope.
It isn't.
No.
Wow.
It's one or the other.
Both sides of the horseshoe magnet, they couldn't be pushed together, right? Because they repel.
They magnetically repel, but you can put them in a vise and crush them together, and they don't like it, but it will hold them together.
But they both pick up your paper clips and things, right? And your iron filings, they both pick it up, even though one is a plus charge and the other's a minus charge?
Yeah, because they push the electrons away. The things usually diamagnetically respond to an applied magnetic field. There has to be some ferromagnetism in the material you're going to pick up, because your magnet is iron, or in the simplest case, I mean, we get all these rare earth magnets nowadays, but it has to pick up, it has to have some magnetic ability to pick up in order to be attracted to it. A horseshoe magnet will not pick up a piece of aluminum.
Is that right? Well, okay, yeah. But aluminum makes good rocket fuel, and that's a totally different process, I know, and it's ground up. I don't know why.
Yep.
Interesting. Okay, we're going to the moon. We're off the ride. I can unbuckle my seatbelt.
One last comment. I think Tom Totten's on the chat, and he said a pound on a nail and make it magnetic, ? I think.
No, pound on a nail and you make it lose its magnetism.
Right.
Yeah, I think it loses it. Yeah. So I think he had it backwards. He may chat on that later, and I'll let you know.
Okay.
Okay.
So we just passed full moon, I mean, we just passed new moon last, I think, Friday. The excuse me, I said that wrong. We just passed last quarter, last Friday. This coming Saturday, we will see the full snow moon on February 24th.
Hmm.
And today, February 19th, we see the waxing gibbous moon just past first quarter. This is what it looks like at 7 o'clock tonight.
Oh.
Now, there's been a flood of really good
Whoa.
lunar pictures. This is by a guy that has a 400 millimeter Zeiss Cassegrain in Europe somewhere. Uwe Mailing.
It's 16-inch, 16-incher, Jerry.
400 millimeter.
Yeah.
Does absolutely excellent work. Great image. He must have great seeing and stuff.
Yeah.
Now, this is the crater Arzakel. Very nice. You can see the cracks down here. I can just see these visually with my 6-inch refractor, but he's got them in a photo. This is absolutely outstanding work. There's a couple of people that produce, and they share these on Facebook. They're Facebook friends. It's quite a group of astronomers on Facebook. So this and Arzakel is,
yeah, it's one of those in the triplet.
It's right there. That's it.
That's it. Okay.
No, no, the one lower, the lower one, right there.
That one, yeah. So there's a one off to the side right there, and that one is captured here also. And then the other thing is this is the Apennine. This is Archimedes, Autolycus, and Aristillus on the Sinus Lunicus by Uwe Melling also. So that, let's see if I can go back and look.
That's just amazing detail.
Yeah, that's up here. It's 2 craters up there. There's the gap in the lunar Apennines.
Look at the little lit rim.
Yeah.
And Ron, you can tell the newer craters, they came later, you know.
They look like they've hit liquid, but it wouldn't have been magma at that state. It hit solid ground, didn't it?
Okay, good point here. Good question. They were liquid.
Oh, they were.
They weren't liquid before the hit, but the kinetic energy of the incoming mass is so high that once they hit, they generate so much heat that during the collision, everything is liquid.
It liquefies it.
It liquefies, and then it splatters, and then it immediately resets. That's where you get the central peak on the mountain in some craters. That's the resplash coming up, and just as it came up, it froze.
Yeah. The detail, Jerry, looks like an orbiter. And this is that 400 millimeter?
Yeah, this is also one from his
incredible.
400 millimeter. Absolutely outstanding.
16-inch.
Yeah. Now this is Petavius, and this is better seen on a waxing crescent because it's way over on the edge of the moon, but it's still a dramatic thing. This is Batavia. There's Petavius right there. So it's going to have very low shadow right now, but you can still find it. The key thing we're looking at for the next few minutes is going to be the South Pole, where everybody wants to build a lunar station.
A base.
Yeah. So this is, it turns out that at the lunar South Pole, and this is not a photograph, this is from the lunar mapping that I use. And it shows, you can't pick it out because it's all foreshortened down there. But you can see the crater Shackleton, or at least the word Shackleton. There's a lot of words run on each other. There is a crater down here that you can pick out at some librations. And,
yeah, it's hard to pick it out with libation.
Yeah. Libation. Okay. But this is a orbiter picture of the rim of Shackleton. And this is the geographic south pole of the moon, located on Shackleton's rim right here. So that is the prime real estate. I guess everybody wants a view. So they're going to build on the ridge. But recent information shows that there has been seismic activity on the moon. Apparently, Apollo left behind a seismometer, and it recorded a magnitude 5 earthquake that lasted an entire afternoon. Not a sudden shock, but a lot of motion, and a lot of plate movement. So down here, as the moon shrank in the quake, the sections of crust were pushed on top of one another. And they're doing now a surface mapping of the moon's south pole, and that has found that evidence there's the same thing's happening at the south pole. And the arrows here indicate the fault line and the over pushing of one part of the moon onto another.
Jerry, is there any reason for the longer duration of earthquakes on the moon?
There probably is, but I don't have a clue.
Okay.
But there's certainly not any plate tectonics going on up there.
Not to the strength that we do here on Earth, certainly, but there could be. There are different regions of lighter and heavier material. The moon is not homogeneous. It's got what they call mass cons, or concentrations of mass, under some of the big seas on our side, making that side of the moon the heavier side. And so it's hanging down toward us.
Huh.
But and there could be areas of magma that still move and cause something's making the crust move a bit when they get earthquakes.
But that rim you showed us a moment ago, you said was the South Pole. That is where the bottom end of the axis that it spins on would be coming out right there.
Yes, that's right.
And it doesn't wobble like the Earth does, or there's no 23 degrees at all. There's no slight seasons on the moon.
Oh, there is wobble. That's where we were joking a moment ago about libation and libration. If it has the R in it, that's the lunar wobble, and you can go through one wobble each 28 days, and so that it doesn't. Well, this is the best estimate of where the lunar geologic South Pole is. So,
but if what you're describing, then we'd see this with some lit up edge of this rim, and then we wouldn't see it. It'd be all black. Like your what's the word for it? Arctic Circle and Antarctic Circle almost.
This crater down here is always all black.
Okay, so the water is permanently. Got it.
So they want to put things up here so they can get solar power that always shines on the mountaintop.
Got it.
Go down here and mine for ice.
You suppose they're going to look for lava tubes to put the people in?
I don't know. The lava tubes they found are more up in the center part of the equator part of the moon, but I don't know what the distribution of lava tubes is. There's no reason to hide from the sun down here. It's going to be cold all the time.
Well, I read
is the lunar ice, would the lunar ice be an H2O, or would it be a different chemical?
No, it's H2O.
Oh, okay.
It's dirty H2O. It's got a lot of minerals and a lot of dirt mixed with it. Dust probably keeps it from sublimating.
Well, you can get a lot from H2O.
You won't be able to ice skate on it.
No, but they can make rocket fuel out of it.
Yeah, and water, right? And water, rocket fuel, and probably oxygen, huh?
Yeah, oxygen and hydrogen. Hydrogen's the rocket fuel.
Yeah.
And they think there's the same amount on Mars, or the same situation on Mars. On the poles is where you'd find water.
Yeah, well, the poles on Mars are part CO2 ice and part water ice. But there is a crater that we showed a picture of a couple of months ago that is a crater that's full of water ice.
And there's lots of permafrost on Mars too.
Yeah.
So it's distributed, not just at the poles.
Yeah.
I wonder with those ridges that you're looking at, I wonder what the height of those would be.
Oh, I don't know.
Yeah, it'd be interesting. Boy, if they're 50 feet, 100 feet, that's a big push going on.
What was just launched by NASA? Artemis 2 and nobody on board?
No, a private satellite that is on its way to make a soft landing on the moon from a private company, a simple lander.
The picture I saw looked like some sort of a large, oversized snowflake or something with arms reaching out. Is that a lander? It's going to land on them.
I didn't see that.
Okay.
Okay.
I kept seeing it. All right, here we go. Let's go out into deep space now.
Okay, we're going to go and touch on the field of MOND. MOND, as you know, is modified Newtonian dynamics and has been proposed by several physicists from the 80s on as an alternate to the existence of dark energy, dark matter, I mean, not dark energy. So it's a paper published from the University of Seoul in Korea. It's a peer-reviewed paper in the August 23rd, 2023 issue of Astrophysical Journal. And what they're doing in that article is thank you for this information, Chuck. This shows it's a log plot, don't worry about that. This red line shows the prediction of, this is about galaxies and how their outer rims rotate, whether it follows Newtonian dynamics or not. It doesn't. This is the pattern that it shows, and this is due to it. This is the data. This is the pattern that it should show due to MOND. And and this is so it does deviate from the Newtonian, but MOND has always had a problem with matching this data. As a matter of fact, MOND is considered dead largely because it does not correctly account for the rim motion of galaxies. But the group in Korea decided to try to figure out a more basic thing, because there's a lot of things that go on in the rim of a galaxy, a lot of interactions that are not accounted for. And so they tried to get it down to point sources. So they went through Gaia data, and they found distant binary stars that had, so they were like point sources, and they measured the gravity involved at this distance. So gravity, as you know, drops off as the square of the distance, inverse square of the distance, and it gets weaker and weaker and weaker. And the very strong limit of gravity is very well accounted for by general relativity. The region in the solar system where gravity is not so strong, but not so weak, is accounted for very well with Newtonian mechanics. We still use Newtonian mechanics to fly to Mars, get there accurately after 7 months of coasting. But the idea in MOND is that very, very weak gravity has not been tested. And gravity it may not be continuous. As general relativity said, it might be quantized. It might, at the lower limit, it might break up and act differently. And so now they're trying to decide if that's happening. And so they're doing it with point sources. They went through Gaia data, and they found, I think, 265,000.
And that link I sent you, Jerry, is where a subsequent study used their same Gaia data, but applied more quality control to the measurements that were poorer quality as far as the velocity of these binary systems.
Yeah.
And they found no evidence of MOND.
I read that article. It's a good article, and it did do exactly what Chuck said. But the conclusion was we can almost eliminate the results from the Seoul paper. So that's the right thing to do. They will tune it, and they will go through it. And in back and forth analysis in physics and discussions like this, a lot of things that were good ideas have been thrown in the dust heap because of that. I'm remembering, for example, the most embarrassing one was Gran Sasso, which did some experiments and claimed that actually neutrinos travel faster than the speed of light, which sparked the physics joke about a neutrino walked into a bar and said, "Why is it so dark in here?" Yeah. So
and cold fusion.
Oh, cold fusion.
Yeah.
Now there is cold fusion, but it doesn't happen at the rate that it can generate useful energy, but
Really?
it does happen.
We can't, we
But
can't,
anyway,
we can't make it happen here on Earth.
oh no, it happens on Earth in the lab. You can make it happen. There's a guy at UCLA when I was there. I forgot his name now, but he was making it happen with collapsing bubbles, super bubbles in the sonic shock would produce little bits of cold fusion.
Wow.
Anyways, and that effect is heavily studied. By the way, you know, fusion energy has, as an aside, fusion energy has just achieved break even plus. They get more energy out of it now than they put into it. So it's making progress. In 1975, it was the energy source of the future, and people claimed it always would be.
But now the
Very
difference,
quick,
go ahead, gentlemen.
Okay, so anyway, the result of the Soul paper, which the other paper that Chuck referenced, seems that they did a better job of reducing the data, and so we're letting those two cats fight it out. But this is the deviation that they see from Newton at low accelerations, and this is a quadratic Lagrangian prediction for the deviation. So it's close to that. So they see this deviation, and the MOND based on Lagrangian dynamics fits that somewhat. So hang on, the issue's not over.
Well, before you leave this, Mr. President, are we looking at a binary? One of them, the smaller one, is orbiting the other?
Yes, this is an artist's rendition of a binary. I don't think
a triple.
What's that? This is
like a triple.
Yeah.
Triple. Oh, there's
and
two.
This is all, if I'm not mistaken, this is all to predict the outer motion of galaxies.
No. They're trying to decide if Newtonian dynamics needs modification. And so what they want to do is they want a real clean case with point sources, and they want to try and measure the drop off in intensity of gravitation outside of our solar system. So this distance is way bigger than our solar system.
Okay.
They want really wide binaries.
Right, really wide binaries. And because they want to see, and then they measure because the period that they measure out here is going to give them the strength of the magnetic or the gravitational field.
Okay.
So that's it. They're after fundamental things.
But they're zeroing in on our galaxy, not some other galaxy.
No, this thing. This is other galaxies outside our own. These are each dot is the rim of a galaxy.
Somehow they can detect binaries in other galaxies.
No.
They
this
can't.
particular study is binaries in our galaxy.
Oh, I see. Okay.
Yeah, but this curve that you see now, that is galaxies, and that's measured redshift of one side of the galaxy compared to the other side of the galaxy. So there's a lot of stuff going on in there.
Huh.
So and MOND does not obviously calculate that correctly. Both MOND and dark matter have problems in different ranges, and they're trying to resolve that. So it's an active area of research, and I can't give you a definitive answer yet of what's going on. The consensus among physicists, as if popularity was a driver, is that dark matter is the culprit, not MOND. But
well, maybe there's less. Perhaps there's less dark matter out in the fringe area at the edge of the galaxy.
Could be.
And obviously the binaries or the stellar systems like our solar system, we probably are affected by dark matter too. When you think if there's extra matter, extra mass in this,
it's passing right through us right now in massive quantities if it exists. Okay, this is the James Webb Space Telescope, all wrapped up as a origami puzzle, soon to be unwrapped as it's leaving Earth.
Okay.
Nice picture.
Yep.
This shows that infrared The James Webb Observatory has all of this redshift out here between half of a micron and almost 30 microns. The Hubble Space Telescope can see this part, and our eyes can see probably here to here. My eyes can probably see here to here.
And with glasses.
So the issue they're looking at here is there's a lot of stuff going on with James Webb's first data coming back. And at first they said the age of these galaxies was they were so young, for example, that there just couldn't be. So they had, measuring the redshifts, they had redshifts of 9 or something out there. And redshift of 16.7.
Yeah, makes sense.
And with an object called CEERS 93316, which is shown here in this picture. You'll all recognize that. So these were just impossible dates. There's not enough time to form a galaxy. So they've been looking at that, and a lot of the models that they're using to look at it have how the universe behaves right now molded into it. And they're deciding that some of these things are wrong, so they're redoing it. They've recalibrated the redshifts, and the one that had 16.8, was it 16.7, now has 9. So
yeah, they got better spectra.
Yes, they've got better spectra, and they have 3 starbase theories that explain the JWST early galaxy data. The galaxies are too bright and too many. The brightness, and it all has to do with the fact that the stars are different. The stars formed out of early dust, and they're all very giant stars with they're massive stars with very intense solar winds, and so it blows the dust away in the early galaxies. And that's
low metallicity.
What's that?
Low metallicity too. That lets
them they're very hydrogen rich, and they blow the dust away, and that's why these things look bright. There's no dust. But shortly after after they age, those big stars have short lives, and when they die, then they're in the redshift range of 4 to 8, and those are very dusty. And so they're able to now account for that. This is a galaxy. This is CR7. It was the brightest known galaxy in the early universe. And this image shows an artist impression of CR7, not a photograph, excuse me. So, and this is very dusty. So that didn't fit with these bright galaxies, but the fact that these go through a very fast stage with very big stars that blow the dust away, and then the stars die and they create enough more dust. And so they're able to now account for the missing dust. And this is an example of a dusty galaxy in our present universe. This is NGC 3717, taken by the Hubble Space Telescope.
Wow.
It leads to a basic question I've recently entertained in my brain, gentlemen. Gas and dust. Gas, by nature, if not by definition, you shouldn't be able to see at all. Dust is little solid particles. Where did they come from?
Most of them come from my dog.
Fun. Gas.
When did I lose control?
Gas. I mean, chlorine gas has a greenish color, you know. It just all depends on the molecular structure and how it interacts with light, the electron shells and stuff. And dust is just where you've got solid pieces of stuff that have congealed. That's all it means. You know, you've got carbon and silicates, like carbon dust.
When stars explode, or when they don't quite explode, they just throw off their outer layers. They don't just throw out individual atoms. They throw out clumps of atoms in the form of minerals.
Sure. That would be your dust.
Yeah, that's the dust.
Okay, well, we're almost out of time, but is this a galaxy we're looking at here?
Yes, it's an edge-on galaxy.
Can I make a comment from Tom Totten again, referring back to the magnetic discussion we had, he went on to van.physics.illinois.edu. It says that hitting iron aligns magnetic domains with each on trains. When trains are rolling over the tracks, they're hitting the rails, and they found that they were slightly magnetic. So yeah, and so I don't know if that qualifies for banging on the metal or if it's just aligning it because it's traveling one direction.
No, it's not banging. Banging undoes the magnetism. When the trains roll over the rail, they get hot. And when they lose the heat, the random motion, they're in the magnetic field of the Earth. They pick up that magnetic field.
Oh, wow. Interesting. Okay, there you go, Tom.
You did that whole piece without mentioning magnetars, monsters out there in space once.
Those are a much more complicated thing, and I think there's very little known about that, at least by me. So
well, all stars, including ours, have some magnetic field, but the ones that are really crazy go crazy, don't they?
Yeah.
The magnetars. Well, fascinating stuff. Well, I can't wait for the final exam.
I can.
Remember this picture from the a current loop or a path of an electron doesn't have to have metal there. But picture this wire, and then you take this wire and you crumple it all up into as tight a ball as you can. And it's all crumpled up, and then you send a current through it. The magnetic field from that crumpled up wire is going to be a very complex field to map.
Yeah.
So that's what you get in stars.
That's exactly right. That's what you get in stars, because the plasma is all crumpled up.
Is the letter B named after Bohr, who came up with his atom?
No.
I don't know that it's after anything, but if there's a famous law which someone mentioned earlier, BO and Savart.
But I'll tell you another element that definitely would carry electricity just like iron, if not better, and that's what's in our walls, copper.
Yeah.
But others, aluminum.
Copper's not ferrous. It won't. When you line up its atoms, as soon as the magnetic field goes away, they don't stay lined up.
Is that right?
Yeah.
And copper, there's a really interesting from this diamagnetic effect. I remember Dale Loudermilk used to give a display where he would have a copper tube, a copper pipe, and he would drop a magnet into it. And you expect a magnet to fall out the bottom, but it takes forever for the magnet to come out, because as it moves, it generates a field that then has an opposing field generated by the copper, by the electrons in the copper, and it actually holds the magnet up quite a bit. And slows it down.
That was always a favorite in my demos too, Chuck.
Yeah.
So the magnet basically produces eddy currents inside the metal. Okay, that it creates opposing fields to slow the magnet down.
Wow.
But has the value of iron gone up like copper has?
The value of iron?
Well, people are stealing copper, and the pennies aren't made of it anymore. Everything is iron. Is there more iron than there is copper?
Yes.
No, I think the value of iron is still ironclad.
On that note, ladies and gentlemen, we're going to have to terminate. This is awesome. Thank you, Mr. President, and the rest of you, and take care of yourselves and your wives, and don't get too wet. We'll be back together next Monday morning for number 158. Then we start our 4th year of telecasting, or whatever this is called. Zoom out. We'll see you next time. Thank you.